Okay, so in front of you, you should have your PowerPoint for the motion graphing, and you need to have something to write with. And I'm going to go through this. I want you to write down what I say, what we talk about, and then in class tomorrow, we will do some practice with the motion graphing. Okay, so let's go ahead and get started. All right, so when we're doing the motion graphing, we're going to be talking about two different types of motion. And I'm going to show you how to graph each of the two different types of motion, and then I'll do a summary at the end of the two different types. So the first type of motion is objects that are moving at a constant velocity that have zero acceleration. And an example of that would be like a car moving in cruise control on the highway. Something like that would be a constant velocity motion. And then the other type of motion we're going to talk about is objects that are accelerating. So velocity is changing at a constant rate. And examples of those would be objects that are in free fall, so moving away from the earth or moving towards the earth under the influence of gravity. Or it could be a car pressing on the accelerator at a constant rate. That would be another one, so the car's speeding up at a constant rate, or slamming on its brakes so that it's slowing down at a constant rate. So those are all different types of examples. And the way that we graph these two, the graphs are going to look different. So we're going to be looking at both different types of motion and the types of graphs. When you go to graph that motion, what do you get out of that? So first of all, constant velocity graphing. So for a constant velocity motion, when you go to graph the position time graph, so we'll take a look at that. So first of all, the position, we're going to graph on the y-axis, position as a function of time, and we're going to graph time down on the x-axis. And for a position time graph for a constant velocity, because that object is not speeding up or slowing down, every second that passes by, the object moves the same distance. And so if I were to plot that over here, that means every second that passes by, the object goes the same distance. Right? So when I plot the position time graph for constant velocity, I end up getting a straight line out of that. You'll do a better job with a straight line than I did right there. So that's what you should know. So a position time graph that's a straight line indicates constant velocity. The slope of this line, which is the rise over the run, so if I calculated the slope by taking 2 points and calculating the rise over the run, which is the way you know to calculate slope, that slope would be the actual velocity, whatever the constant velocity is. The way you can know that is because the position is in meters and the time is going to be in seconds. So the rise, which is this direction, has units of meters, and the run, which is this direction, has units of seconds, and that gives you a number which is a meter per second, which is a velocity. So looking at the units of the slope are going to help you determine what that slope actually is and what that slope represents. It's going to be a real clue. So that's one hint that you're going to want to write down, that the units of the slope, the units of the rise over the run, are going to be really important for you figuring out what that slope represents. So in this case, the rise over the run is meters per second, so that slope is the velocity. So if I say there's a car going at, here's an example, a car moving at 7 meters per second. When I go to plot that, 1, 2, 3, 4, 5, 6, 7, so there's 7. And then I'll do another one. 1, 2, 3, 4, 5, 6, 7. There's 14, right? And then let's suppose this is 1 second and this is 2 seconds. So if I go to plot this, that means after 1 second, the car has gone 7 meters. After 2 seconds, the car has gone 14 meters, another 7 meters. So that would be a line. And the slope of that line would be equal to 7, rise over run. 7 over 1, 7 meters over 1 second, or 7 meters per second. Okay? So that's how that works. So you get straight lines. The slope of the graph is the velocity. And you can also see this from this formula, velocity's displacement over time. And so if you look on a graph, a straight line graph like we had, you can take your displacement, which is going to be your rise, basically. That's going to be your displacement divided by your time. Okay? So that, and then you can find your displacement by taking your first and your final position and subtracting the two. So that's that difference on the graph, the rise part of the graph. For the velocity time graph, so here's where it gets a little tricky. So we're going to now talk about what does the velocity graph look like if I plot velocity versus time. So if I'm a car moving at 7 meters per second, right? Every single time I'm moving at 7 meters per second. So if I want to plot what my velocity is, here's 7, and I'm going to all the time be going 7 meters per second. So any time down here, I'm at 7 meters per second. So this is going to be a horizontal line. And the value of that horizontal line, whatever value it hits at, that's the speed. That's what velocity I'm moving at. If the car was going 2 meters per second, that plot would look down here, 2 meters per second. And it would be straight like that. Okay? So when it's a velocity time graph and you have a constant velocity, you're going to get a horizontal line when you plot that. So you have to just think about it. The slope of this horizontal line is the same as the slope of any line, and it's 0. Any horizontal line, pardon me. And the slope has units of meter per second per second. So the rise over the run would be meters per second, which is meter per second squared, which we all know is an acceleration. So what this is telling me is that the slope of this graph is 0 meters per second squared, which means that the car or the object is not accelerating, which is of course what's going on because it's a constant velocity. So the car is not accelerating. Okay, so the slope is 0. If we wanted to plot the acceleration time graph, I'll just do that one right here. The acceleration is in meters per second squared. The time is in seconds. And it's 0 all the time. So it just stays down here 0 the whole time. Down here on the 0. That's the acceleration time graph. It never changes because this is a constant velocity object. It has no acceleration. Okay? So that's what those three graphs are going to look like. A straight line for position time, a flat line for velocity time, and for acceleration time, you can see it over here, 0 the whole time. Okay? Now, slightly more complex is when you get constant acceleration, so the velocity is now changing. When you have that situation, the position time graph is not a straight line anymore. The position, which is still going to be in meters, and the time down here, which is still going to be in seconds, now you see that if you watched the object, every time period, the position would get farther and farther away because the object is speeding up, right? So if I think about plotting something where here the position, 1 second later the position's close, 2 seconds later it's a little bit farther away, 3 seconds after that, you know, it's gone even farther, the next second after that it's gone even farther, the next second after that. So if you think about what that looks like, that's not a straight line, it's actually a parabola, which hopefully you recognize that. So when you have a constant acceleration motion, the object is speeding up, so it's covering more distance each time period, and you end up getting a parabola out of that. The equation actually takes the form of a quadratic. So here's where I want you to think about what we did in the lab, and then think about what I'm saying here. So we already know that equation 2, x final is x initial plus v initial times time plus 1/2 at squared. That's equation 2 of our equations of motion. And that is a parabola. And it takes the form of y equals ax squared plus bx plus c. Or if that's confusing, let me take out the x's and make them t's. I don't want to confuse you by making the a into... Right? So this is the form of a parabola, ax squared plus bx plus c, or at squared plus bt plus c. So you can see that the second equation of motion is in the form of a parabola. And this capital A, whatever's in front of the t squared, is going to be 1/2 acceleration. And the capital B, whatever's in front of the t, is going to be your v initial. And the capital C is going to be your x initial. So when you go to plot the position time graph, and you see that there's a parabola, your x initial is going to be right here, right? Your v initial is actually the beginning slope, and to get the acceleration off of this is a little bit more complex. But that's the general idea, that we have a quadratic and it follows along with the equation of motion. So that's what I wrote right there. The average velocity is found by the displacement over time. So let me go back and write this down. So if I have a parabola, if I wanted to find the average velocity, like between this time and this one right here, t1 and t2, if I say find the average, then I just need to figure out the displacement. So this is x1, and over here is x2. So I would just do the displacement, x2 minus x1, over t2 minus t1. So it's really, you know, the displacement, which is this, over the time, which is that. Okay? So that's how I would figure out the average velocity. The instantaneous velocity is a little bit trickier. We'll have to practice that in class tomorrow. But to get the instantaneous velocity, which is the velocity right at any instant in time, you're going to do, since we're not doing calculus in here, and those of you who are in calculus will recognize maybe that I'm taking this, the derivative of this. But if I want to know the instantaneous, let's suppose I want to know the velocity right at this time, t1. I want to know how fast is it going. Then what I have to do is I have to draw what's called a tangent line. And a tangent line is a line that skims the graph only at that one point. That's what we call the tangent line. So it's a straight line, it skims right on that graph, it touches only at that point. And I have to figure out the slope of that tangent line. So if I can do that, the slope of the tangent, the rise over the run for the tangent, I can see what the instantaneous velocity is. So you can see right here, there's this tangent line that I've drawn right here will have one slope. If I come up here and I draw a different tangent line, for that point, it's much steeper because the tangent lines get steeper as the graph moves along in time. That's because the object is speeding up. It's changing its velocity, and so it's getting, the velocity is getting faster and faster. Okay, so the velocity time graph for a constant acceleration motion, since the object is speeding up, if I were to watch the velocity, I would see that the velocity is getting larger and larger at a constant rate, and that is straight line. So for this one, you're going to get a straight line, a velocity time graph. The slope of this line is going to give you a unit of meter per second over seconds, which is an acceleration. So the slope of this line tells you the acceleration of the object, the rate at which its velocity is changing. The equation for this line takes the form of any equation for any line. So I'll do velocity in meters per second, time is in seconds. Let me redraw this on here real quick. So if you look at our first equation of motion, v final is v initial plus at. That's the first equation of motion, just written in a different order.